Let's dive right into this explainer. If you've ever stood next to a massive industrial facility, like a power plant or a refinery, you've probably looked at those endless miles of thick steel piping. On the surface, the whole thing looks completely static, right? Like it's just frozen in time. But actually, underneath all that steel, there is a constant, totally invisible battle of physics going on. Today, we're going to uncover the hidden physical forces that are constantly twisting and stretching these massive industrial pipelines. And we'll take a close look at the mechanical heroes designed specifically to stop these forces from tearing the entire system apart.
Here is how we're going to break it down today. First, we'll look at the hidden forces inside pipes. Second, understanding the Bourdon effect. Third, how expansion joints come to the rescue. Fourth, the different types of expansion joints. And finally, essential accessories and upgrades.
All right, Section 1, Hidden Forces Inside Pipes.
To really understand the hardware we use in modern industry, we first have to understand the massive problem created by high-pressure liquids and gases just rushing through these enclosed spaces. Now, you might be wondering, why not just use rigid, completely immovable pipes everywhere? Well, think about what actually happens when you pump something like 60 bars of pressure into a pipe. That internal pressure acts like a physical force that stiffens the material. It's kind of like when you bend an empty plastic bottle. You instinctively squeeze it in the middle because the internal pressure is fighting that bending. Or think of a guitar string. As you pull it tight, it becomes way less flexible from side to side. In engineering, we call this stress stiffening, and it completely changes how a steel pipe behaves in the real world.
But it doesn't just get stiffer. The pipes actually grow. For example, if you take a standard 10-meter pipe, the internal pressure might only stretch at about 2 millimeters. That doesn't sound like a big deal, right? But let's scale that up. If you pump 50 bar into a 32-inch pipe that is 50 meters long, it causes an axial elongation of exactly 12.729 millimeters. Now, a jump from 2 millimeters to nearly 13 might still sound like a tiny fraction, but make no mistake, that movement is backed by immense force. If you don't account for this shift, it is entirely capable of tearing solid structural anchors right out of the concrete, which would just be disastrous for the entire facility.
Moving on to Section 2, Understanding the Bourdon effect. The Bourdon effect is this really fascinating phenomenon where internal pressure fights against the natural deformation of a bent pipe. Basically, when a pipe bends, its cross-section naturally flattens out a bit into an oval. But when high pressure flows through it, that internal pressure pushes outward in every single direction, trying to force that oval back into a perfect circle. And as it tries to recover its original circular shape, the curve of the pipe literally attempts to straighten itself out or open up. This effectively increases the stiffness of the curve and creates massive structural stress on the whole system.
When you look at a Caesar 2 software simulation, with the physical movement magnified 1,000 times, it's pretty wild. You can clearly see how the curve physically translates and rotates as it fights to straighten out under the pressure. And if that pipe happens to be connected to sensitive equipment, like a compressor or a turbine, this roto-translational movement can cause load variations of up to 117%.
Section 3, Expansion Joints to the Rescue.
So, the absolutely crucial point here is figuring out how to stop this theoretical movement and immense pressure thrust from causing actual, real-world catastrophic failure. To solve this, we rely on a beautiful core principle of pipe stress engineering. As experts L.C. Pang and Pang point out, pressure elongation generates a displacement that is a self-limiting load. Now, unlike a primary load, like gravity, which just keeps pushing until something completely snaps, pressure elongation actually stops once it reaches its maximum potential axial displacement. This bridges the gap between those invisible forces and our physical hardware. It confirms that if we can simply give the pipe enough room to safely stretch out to its absolute limit, the entire system survives. And we give it that exact room by using expansion joints. These are highly flexible components inserted directly into the pipeline that behave exactly like mechanical springs. They seamlessly compensate for thermal expansion, pressure elongation, and that trippy Bourdon effect, all without transferring fatal reaction loads back onto the sensitive, expensive equipment attached to the network.
Section 4, Types of Expansion Joints.
Before we check out the specific models, we have to understand the battleground itself. We need to distinctly contrast axial movements, which compress or extend straight along the pipe's longitudinal axis, against lateral movements, which shear perpendicularly to the pipe. There's also angular rotation and torsional twisting, though I should note that twisting is strongly discouraged because it totally destabilizes the joint.
First up, we have the axial expansion joint. This is definitely your most straightforward and economical solution for simple compression and extension. It handles straight-line growth perfectly. However, it doesn't restrain the internal pressure thrust on its own. So if you're going to use this one, the piping designer has to provide massive, separate main anchors out in the facility just to keep the pipe from blowing apart.
Now, to handle more complex stress, we use the gimbal expansion joint. The external hardware on this thing operates remarkably like a universal joint on a vehicle's drive shaft. It's specifically designed to safely accommodate angular movements in any plane, and crucially, its structural hardware actively resists the pressure thrust, which completely saves you from needing those massive external anchors.
And for truly extreme situations, we bring in the universal expansion joint. This setup utilizes two separate flexible bellows that are separated by a central pipe spool. It is the absolute heavy hitter for tackling massive lateral shear movements right alongside axial compression and angular deflection. Finally, Section 5, Essential Accessories and Upgrades. The beating heart of any expansion joint is the bellows, that wavy, corrugated metal section. The spring rate, meaning how much physical force it takes to compress it, and its total life cycle are entirely dependent on these precise geometrical variables. The pitch between the ridges, the depth of the convolution, the thickness of the metal, and the number of plies all dictate whether this joint is going to survive a decade or fail in a week.
Here is one of the cleverest upgrades in piping design, the multi-ply bellows configuration. Instead of just using one thick, stiff sheet of steel to hold back high pressure, engineers nest several super-thin tubes inside each other before forming the corrugations. A multi-ply bellows can handle massive pressure, but because each thin ply acts individually when it bends, it drastically lowers the spring rate and exponentially increases the cycle life. Some of these are even designed as two-ply testable setups. That means if the inner ply fails, the outer ply steps up as a redundant backup, safely holding the pressure until repairs can be made. It is absolutely brilliant.
Lastly, we have to talk about the external restraint hardware, limit rods versus tie rods. They look incredibly similar, but confusing them can be disastrous. Tie rods are designed to actively contain daily pressure loads and hold the whole system together. Limit rods, on the other hand, are purely backup safety devices. During normal, everyday operation, limit rods do absolutely nothing. They only engage to restrain massive forces if a main anchor in the facility catastrophically fails.
So what does this all mean for us? Well, this explainer reveals that underneath the quiet, static exterior of every industrial plant lies a constant, completely invisible battle of physics. Between stress stiffening, elongation, and the Bourdon effect, thousands of pounds of force are constantly trying to tear pipes right out of the ground, and they're held back only by the ingenious engineering of multi-ply bellows, gimbals, and tie rods. It really leaves us to wonder, knowing the staggering forces at play inside these massive pipes, just how much trust do we put into these hidden mechanical heroes every single day? Thank you for joining me on this deep dive into the hidden physics of industrial piping. Keep questioning, keep learning, and I'll catch you in the next explainer.